The discrepancy between Newtonian estimated mass in spiral galaxies and the observation of star and gas kinematics is well established. The rotation curve relates the square of the tangential rotation velocity of particles in orbit around spiral galaxies to their galactocentric radius. The RC is measured along the major axis of the galaxy. In general, the RC starts at the center of the galaxy where there's a lot of mass, a supermassive black hole. The rotation velocity there is around 5,000 or more kilometers per second. From there on out, the stars rotate in a declining Keplerian fashion down to a minimum, which generally is achieved within a parsec. At this point, the rotation velocity is so low that it looks like there's no mass inside this radius at all. Then the mass in the galaxy starts up again, and it's usually pretty close to a straight line, increasing up to a knee. From the knee outward, the rotation curve can rise, be flat, or decline. Traditionally, the focus has been on accounting for gaseous RCs that are flat in the outer region immediately beyond the knee. However, observations also include rising RCs, declining RCs, an abrupt change in slope at the extreme outer region in many galaxies, and rotational asymmetry with non-relativistic velocities. The RC is an excellent tool to evaluate galaxy models because it models the mass distribution in spiral galaxies. Papers that provide a summary of the knowledge of RCs are these and these. The gas RC with filled diamonds here, as you see, starts close to the center but still near that gap, increasing, but there are bumps here, it's not necessarily a straight line, up to a knee. From there on out, in this graph, it goes straight on out, and it goes out quite a ways. The H alpha is ionized hydrogen, which is near stars. So this then is the star rotation curve, and it ends about here, which is close to the knee. And you'll notice that the gas hydrogen continues on out. The Keplerian decline in the center implies a mass distribution centered and very large relative to its close neighbors. That is, a supermassive black hole where the mass of the supermassive black hole is calculated using the slope of the Keplerian declining curve. The RC is rising from the minimum outward, implies a slowly increasing amount of mass near zero is affecting the RC. That is, if there is no mass effect of the central region around the supermassive black hole on the outer region. The mystery is, why is the disk centered around the supermassive black hole when the calculations show no mass effect of the black hole on the disk? Or, what is the relation of the central mass to the disk parameters when no relation seems to exist? Other discrepancies of accepted models are shown here, where the knee could actually be a very sharp point, not a slowly varying point. Secondly, it seems that a piecewise linear fit is a better fit than the varying, smoothly varying models. We have some 50-odd galaxies in our sample. The ones with the error bars are 16 of them, and they have a better distance calculation, so we put error bars on them. And just to keep things kind of clean, they're the only ones I put error bars on. You'll notice that these galaxies down here, and there's not many of them, but they generally tend to be ignored by other papers. Here we're including everything that has an RC. You'll also notice the slope of this line is approximately twice the slope of that line, The slope of that line is approximately twice the slope of that line, etc. This is the STOE model, where we have three forces acting on matter within the disk, say, of a spiral galaxies. We have gravity, which is the inward pressure. We have the strength of the source, which is an outward pressure, as we explored in other videos. And we have a third term, which is the strength of other galaxies' effect on the host galaxy. In this video, we look at the first approximation, which is the first two terms of the equation, that is to say, k is 0. M and L are related, and doing the little math, we end up with this. The rotation velocity squared is proportional to the luminosity, where this is the slope of the line, and that's an integer. The following graphs show the STOE piecewise line compared to galaxy actual. The reference for each galaxy's data is given. The luminosity is determined by the source strength at the center of galaxies. Another video explores the source strength to the central mass relation. Therefore, the center mass is linked to the outer galaxy parameters, a result conventional physics recognizes but cannot explain. A universal rotation curve model has been presented for a large sample that revealed that only luminosity of the host galaxy dictated the RC. Independent efforts supported this URC model. The L term in the STOE indicates source strength serves the same place as dark matter in the RCs. It also is interpreted as a subtractor to the mass effect. Therefore, the gradient of the scalar potential density is the missing mass. The decreasing scalar potential density is a declining force on the surface of matter outward from the center. This causes the metallicity radius relation, like fractional distillation separates molecules. Approximately 66% of the sample galaxies have A = 4 or A = 5. If we take A = 4.5, then the equation reduces to, as you see, just one constant being proportional to v squared. Further, 66% is a commonly accepted sample for other papers. However, this has a higher uncertainty. The effect of the A value is to broaden the applicability of the parameter to L relation. See the asymmetric RC video. This kind of relation is what is needed for the Tully-Fisher relation to determine distance. The peak at the end of the rising region, that is to say the knee, is near the maximum extent of the luminous matter. Therefore, the rotation velocity at this point is a better indicator of the value for use in the Tully-Fisher relation. You remember the Tully-Fisher relation uses the rotation velocity near the end of the rotation curve. The rotation velocity at this point in flat RCs is nearly the same as at the extent of the RC. Using this value of R3 at this point allows the Tully-Fisher relation to be applied to rising and falling RCs also. This is the paper that all the math and science is presented.